Our next presentation comes from Dr. Tony Hay. Dr. Hay is the Chief Data Scientist at the Rutherford Appleton Laboratory and founded the Scientific Machine Learning Group at the lab. The group is working with the Alan Turing Institute in applying machine learning technologies to the big scientific data generated by the Diamond synchrotron and the CIRO-EM facilities. In 2020, he chaired a US DOE subcommittee that proposes a new Office of Science initiative in AI for Science. He is a fellow of the Association for Computing Machinery, the American Association for the Advancement of Science, and the Royal Academy of Engineering. Dr. Hay is the author of several books, including The Computing Universe, A Journey Through a Revolution, published in 2015. In 2005, he was awarded Commander of the Most Excellent Order of the British Empire by Prince Charles for his service to science. Today, Dr. Hay will briefly review three major challenges for scientists, followed by an overview of how research scientists are exploring the use of AI technologies and analyzing their data under the banner of AI for Science. The talk will conclude with a vision of how this AI for Science agenda could be truly transformative for experimental scientific discovery. Dr. Hay, welcome, and thank you for joining us.
Thanks very much, Brian. Can you hear me okay?
Yes, absolutely, and I see your slides.
Okay, great. So, what I'll talk about today is AI for Science, and I'll talk about what we're doing at our national lab near Oxford, the Rutherford Appleton Laboratory, where we have big machines, synchrotrons, neutron sources, cryo-EM facilities, very similar to the resources you have at the DOE labs that we're familiar with at Berkeley, Argonne, and Oak Ridge, for example. So I'll come back to the US scene at the end, because I think it's a very exciting point we've got to. So without more ado, let me just explain the context. And the context is, if you like, the data deluge. There's a paper I wrote long ago in 2005 or something. Now we have a much greater data deluge. This is the lab, and you see we have a diamond light source, which is a synchrotron like the APS at Argonne, slightly smaller. We have an electron microscopy facility, which does material sciences and molecular science. We have a neutron source, which is a spallation source, and we have a collection of high power and high resolution lasers in the central laser facility. We also host the Tier 1 support for the Large Hadron Collider, the GRID PP experiments, so there are many petabytes of data processed on the lab site. And we also host a Jasmine super data cluster service, which is if you like, a data intensive computer architecture and it hosts most of the environmental science data that goes into the IPC forecast, for example, as well as the new Sentinel satellite data, which is petabytes a year. So there's a lot of data sitting on the site. And this is just one sort of indication of what goes on, which is the actual rate of increase of the data is increasing, and the doubling time of the data has been, in the last decade, doubling much faster than Moore's law. And of course, now we're having computer upgrades, we're having new detector upgrades, and so literally, scientists are now really drowning in data. They can't take their data home on a USB stick anymore. So actually, what do? How do they get it to their university? How do they store it? There's lots of data science issues. And then how do you analyze it? And that's the real issue that we're trying to address. Can we make science more effective, more intelligent by using AI and machine learning? So what we have, AI and machine learning for big scientific data is usually abbreviated as AI for Science, but it really is a mixture of techniques. So just let's be clear that it's not purely AI. AI includes machine learning. Machine learning includes deep learning. So it's a mixture of all those. And this is what our group, Scientific Machine Learning Group at Rutherford, and our remit is AI for Science. What we're trying to do is apply these techniques, deep learning and neural networks and so on, material science, environmental science, particle physics and astronomy, as well as in the life sciences. And at the lab, we're part of what's the scientific computing department, which also does things like computational modeling. It does metadata, data storage. We archive much of the data taken by these facilities. So there's a lot of expertise in the scientific computing department, and this is the AI part of it. So why can't I get this to progress? I can. Okay, so the focus areas we have in our group, which is led by I should say, Jayan Thiyagalingam, and he and I have set up the group, and he's now leading it to use AI in science. So that's one of the areas where we're using it to do science, to get from all this data, can we extract science more efficiently? There's also a separate agenda. Can we use AI techniques to make the facilities better, faster, and easier to use? And that's the smart facilities agenda, and embedding AI and machine learning at the heart of operations, of accelerators, of detectors, and all these things. So there's many things you can do in the facilities. And lastly, can you use these real exemplars of really big data problems with using the AI and machine learning techniques we know about? Can we use them to advance AI, to make understanding, make it more transparent? Can we improve it? Can we get new algorithms when we find out what doesn't work, what does work? And so I'll come back to that with the benchmarking. But let me just give a couple of slides. First of all, about the use of AI in science. I'm having trouble. Oh, that's better. Don't know what the problem was. Okay, so what we're trying to do is use AI to understand experimental results, and this is the sort of thing we've been doing at the lab. We've been on the top, you see cryo-EM extracting from thousands of images, very pale images, very faint images. You can do clever things, and Nobel Prize recently went for cryo-electron microscopy, and using machine learning in various stages, you can really get very detailed predictions of structures. And so, for example, human membrane proteins, which are difficult to crystallize, this is a way you can find their structure. And then there's on the bottom there's material science, inelastic neutron scattering, and it's a very complex system, and can you understand that by using machine learning methods? We've been doing work there. We've also been doing work in the environmental area, looking at cloud masking. Can you detect the difference between reflections off the sea or storms in the desert, sandstorms, from clouds? And again, machine learning and other techniques can help you do better cloud masking. Tracking cell migration as the cells divide and replicate, and also denoising electron microscopy data is one of the applications we've done. So we have a large number of applications in a large number of areas on these different types of facilities. Why is my machine not actually progressing? That's better. Okay, so then smart facilities. Can we improve the science by improving the operation of the detector, the operation of the whole beamline, the whole workflow? You can put AI and machine learning techniques throughout this process. So just as a few examples, can you do on-the-fly data-driven control of X-ray tomography? We've also, with neutron scattering, we've looked at on-the-fly pulse shape discrimination. Can you detect neutrons from gammas and things like that? And also in the laser facility, we've actually made progress in assessing damages to optics, and so you can actually really make better use of your facilities if you can limit the damage that takes place. And so those are just three examples of where AI and machine learning can help you do the facilities. Right. Can we use these real applications to improve AI itself? And that's the general approach of our group. If you like, it's use-inspired fundamental research. So we believe that this is actually, you have to have data sets which are large, you have to have lots of compute, and that's really necessary before you can see how you can improve them. So we have data sets we can make open, and so this brings us to advancing AI with benchmarking. And so this is an example on the right of scikit-learn, and this is how comparing different clustering methods, and you can see there's a considerable spread on this particular example, performance of different clustering implementations. It's the time taken to cluster on the left and the number of data points on the right, and there's a big change as you get to larger and larger data points. So can we use scientific benchmarks to assess AI approaches to doing science? So why benchmarking? Well, we believe it's not helpful for scientists to have a black box which just gives them a number with no error bars and stuff. You need to give them confidence that they understand how it got the result. And what we like to do is a systematic development of these applications. How do they work? How do they work on different architectures? We heard today GPUs, TPUs, and other new chips which are like Cerebras, for example, undoubtedly coming. There's about 100 startups developing chips, some of which will deliver chips that actually have real value. And then there are different machine learning models. Support vector machines have been very effective for small data sets, but now convolutional neural networks, deep neural networks, and so on. And then there are the various frameworks like PyTorch, TensorFlow, scikit-learn, and stuff like this. And so how do all these scale with data? Can you actually use them? These are, I think, important questions for users, but also for architects and for computer scientists. So our agenda for developing the benchmarks is to look at a range of fields: material sciences, environmental sciences, particle physics, and astronomy. Particle physics and astronomy, we don't have the machines on site, but they have large data sets, and they've been very active in exploring the use of AI and machine learning on their data sets. Can we do them more explicitly? Can we do them and understand which approaches work best on which type of problem? And then there's the life sciences, and we see we have lots of life science data generated by our synchrotron and by cryo-EM. Why is it not advancing? Okay, so there are various ways you can organize your benchmarks. Scientific problem, whether it's denoising or tracking, segmentation, these are obvious things. The algorithmic focus, is it classification or regression or inverse problems, and so on. Learning focus, whether it's domain specific or if you're doing high performance computing, surrogate modeling is clearly important. Explainable learning, is it training intensive, inference intensive, all very important. But what I wanted to say was, if you take the algorithms at face value, they don't necessarily, from the TensorFlow and PyTorch, they don't incorporate physical constraints. So can you have AI for science which actually uses machine learning but incorporates things like rotational invariance, energy conservation, and things like that? And how do you put those into your learning algorithms? And that's the sort of thing we'd like to explore for research, and one of our tools to doing that is these benchmarks. So we heard in the first talk today from Simon about the Excalibur project, and this is one of the project's phase one, benchmarking for AI for science at Exascale base, and these are the slides that I got from Jayan, who is actually actively involved in this, along with a consortium which involves several universities, the Diamond Light Source, the Alan Turing Institute, and Oxford, London, and Edinburgh universities. So what are we going to do with this? Well, what we want to do is understand the use of AI in science. Where does it work well? Where do we need improvement? And to scope out a set of problems that could be used, where they can demonstrate what what works and what doesn't work, as benchmarks. And we want to take these from these different fields of science so we can actually relate to a wide range of users, and you can also see how it does in this field, and does the same network, for example, which you've trained here, can you still use it in another field? You can look at transfer learning and so on. And the mechanism for doing this, they're all going to organize a series of workshops in the first half of 2021 to gather input from these communities. And the goal of the project is, if this is successful, is to deliver a report recommending a prioritized list of applications and benchmarks for the different domains. And phase 2 would be then to try and implement that. We also obviously need to look at what else is out there, and one of the organizations which is most prominent is an organization called MLPerf, which is industry supported by people like NVIDIA, Google, and so on. And they have a broad set of benchmarks, and they measure various things, and you can see on their website. But they're looking at problems which are clearly of commercial interest, by and large. Speech-to-text, translation, recommendation, sentiment analysis, these things. Image classification, object detection are relevant to us, as is reinforcement learning, but many of the things they're looking at are not so relevant to us. So their mission is to get fair and useful benchmarks for training and inference performance in hardware, software, and services. It needs to have open source code and publicly available data sets. And what we've set up with Jeffrey Fox and Jayan and myself, we're trying to lead a scientific working group to look at ML benchmarking of scientific applications. And so that's currently, and you're welcome to look on the website and join, and we're trying to meet weekly to establish our initial set of benchmarks. There is another set, which is another working group, which has a different focus, which is the MLPerf high-performance computing benchmarks, where they're looking at these 4 codes and looking at how it will work on exascale machines and so on. And whilst our focus is on using the exascale machines, our really is understanding which algorithms work best for which type of science. So we have a slightly different remit from this science working group, from HPC working group. Okay, so AI for science. What I think it would like to do, since we're at a very exciting stage in the US, the Exascale project, as you heard, has an endpoint when it delivers the first Exascale machine to Argonne on the schedule, but we'll see where that works out. But that's in the next year or so, that's what the time scale is for an Exascale machine. And so what happens after Exascale, because we've also heard today the data showing that Moore's law is actually effectively dead. You have to actually go and do different things, and Americans have chosen to use accelerators, as we heard, as opposed to just CPUs, as the Japanese are doing. So what do we do next for the US advanced scientific computing research in the DOE labs? So what's next after Exascale? The 3 labs, that's Argonne, Berkeley, and Oak Ridge, organized what they call town hall meetings in the summer of 2019. And they looked at, they had over 1,000 scientists and people from industry participating in these town halls. And they looked at research opportunities in science, but they also looked at mathematics and foundations, the data life cycle, software and hardware, and how you integrate with the facilities. And this was deliberately modeled of what they did for the Exascale project. And what happened was that the DOE Office of Science set up a subcommittee reporting to the Advanced Scientific Computing Advisory Committee, which they wanted preliminary results by May and a final result by the summer. And that was the committee that I was tasked to chair, slightly interestingly, and it was a very exciting experience. Most of it, we had one physical meeting in February, and the rest were all, of course, by Zoom. And the issue is that in the US agencies, NSF is the agency who are the priority agency for AI. So they've been doing AI for years. This is France. She's now retired, as moved on from being director of NSF, but this is her quote: "AI is the universal connector that interweaves all of our big ideas. Data science is changing the very nature of scientific inquiry, and AI's use of data has the potential to revolutionize everything we do in science." So this is their vision, and they have a large amount of money because they're the lead agency in AI in the US, and they've set up a number of centers with multiple agencies. So I think you need to think about what DOE's special role is, and that's the same is true in the UK, where we have the Engineering and Physical Sciences Research Council, who fund computer science and have been funding fundamental research in AI for many years, just like NSF. But what the DOE and what our national lab does, we have data sets that are produced by the big facilities, right? And that in the US, they have not only the user facilities and the data sets, but they also have very powerful computers. We have, as you heard, a description of the machines in the UK. We have a number of HPC systems in the UK with the Met Office and with the Archer and Dirac, but we also have the Hartree Center, which actually is focused on HPC for industry, and they're now looking at combining HPC and AI as well. But they also have maths and computer science research at DOE, and also what they're really good at is putting together a team of people with different skills. This is, if you like, the co-design. And what they figured out with the Exascale project is how to work with hardware software co-design with domain scientists. And here I would say it's hardware, software, and algorithms for domain scientists. So that's really where they are. Their role is AI for science at the facilities, and their focus is on that. And obviously, university computer science can collaborate with that agenda, because I think they need to get as much AI expertise as they can. So this is the report. And I'm only going to show one slide from the report. The report is available if you look at the DOE Office of Science website under the ASCAC Advisory Advanced Scientific Computing Advisory Committee. You'll find all the presentations there, including this one, and you can also get a copy of the report. This is one of the recommendations. The major recommendation in the report is that as a follow-on to Exascale, they should go into the same sort of structure that they did for the Exascale initiative, which evolved into the Exascale project. And so we have here at the top AI applications, AI software infrastructure, maths and foundations, and hardware, these four tracks at the top, and it starts with the research program and then moves into an R&D phase before you get to a deployment phase. But of course, from each of these phases, you discover things you didn't know, and so we anticipate there will continue to be some research program as a result of what one finds out in the next phases. And this is a 10-year program with some dates along the top there, starting in 2021 to 2031. The lowest level is what Oscar, the research directorate in the Office of Science for Computing, will be obviously needing to upgrade the leadership computing facilities at Oak Ridge and Argonne and NERSC, and that we anticipate there will be a couple of refurbishments of that, but that budget is not the budget we were considering. And that obviously is collaborating with vendors. But we have a new layer in the middle, which is to me extremely interesting. It's called instrument to edge. And so the idea is that can we actually help the facilities with computing power and also bringing in new ideas, new technologies, new methodologies. And the only way you can do that is with a joint project funded by OSCAR, which actually brings together facilities scientists with the computer scientists and the software engineers in the labs, in the computing part of the labs. And so and there will be hardware to go with it, and it goes from small scale sensors going over the apparatus to relatively significant hardware. And of course you want that hardware to be connected to the leadership scale computing facilities. So that's the structure of the project, and I think I'm optimistic that something like this will be accepted and funded by the government. So at the moment, AI is necessary. Funding is one of the important areas for funding in the US, and you've seen a recent agreement between the US and UK on AI in general. And the specific language used in the White House declaration, executive order on a national AI project, was collaboration with like-minded nations, and so we're hopeful there will be a US-UK collaboration on AI for science. So the Exascale project is winding down, and as it winds down, this will start up with all the sort of things you've heard of today. Okay, so just finishing now, the last thing, what's the purpose of this? Well, you saw that Francis Cordova talked about a transformation of scientific research. So we've already seen Google DeepMind win a competition for producing the best tool for predicting the folding of proteins. AlphaFold uses deep learning, it uses machine learning, and uses large amounts of simulation and computing. Putting that together into a tool, it's the best tool on the market at the moment. One of the things in the future is that you will actually automate the experiments. You'll have self-driving laboratories, which in various different fields, and the laboratory will have a look like this, where there aren't any people there. The experiments are done, and then they figure out what the next experiment they should do. So this is a vision of the future. Obviously, people will be there to help drive it. I don't see it as entirely replacing people. And the other area is that this was my colleague at Microsoft, Jim Gray, had this vision of the literature linked to the data, and then you could add data to it and get more papers, and you could go from the literature to computation to data back to literature. So you could increase what he called the scientific information velocity and a huge increase in science productivity. Well, what you can hope to do with these machine learning and AI techniques is actually do more than just pick up keywords in the literature. You can actually go and find out what the paper actually says. You can have the AI system understanding the equations, understanding what the paper has really proved or not, and you can do much more linking and mining intelligently of the data. So this is actually, I think, an important far future part of AI, but in the 10-year period, we believe that the synergy of big data and big compute and advances in deep learning can really help science be transformed. So I'll stop there. Thank you very much for listening.